The other day, I was just talking about how people are reinventing computing for AI. And just days after, we got something that looks like machine learning is about to be reinvented too. If this new paradigm works on sequential data, we are looking at around 10 times more efficiency than what we currently have for large language models. So we got machine learning 2.0 before GPT-5. Okay, but what is it? Are there actually no caveats? I guess we will find out today how well this new paradigm called Kolmogorov-Arnold Networks, short for CAN, will replace our standard multi-layered perceptron, aka our good old trusty feed-forward neural networks. Before diving into the explanations and equations, have you ever felt like you have a million things going on with AI tools, but no central place to organize it all? HubSpot has put together a dynamic tasked playbook to improve your efficiency and performance, where you can keep track of all the AI tools you use, monitor productivity, and organize AI task assignments. Personally, my favorite section is the Task Delegation Effectiveness Calculator. It helps you see how well your tasks delegated to AI tools are optimized. Check out the link in my description for this free resource. And thank you to HubSpot for sponsoring this video. Back to CAN. It's based on a straightforward intuition. Most AIs right now use some sort of neural network, typically a multi-layer perceptron. An MLP's goal is to pick the correct output for a given input by activating the right neurons, which depends on adjustable parameters called weights. With CAN, the fixed activation functions are converted into a parameterized curve called a B-spline, included alongside weights as trainable parameters. Essentially, CAN makes the activation functions trainable. A B-spline is a curve parameterized by points that act like magnets, pulling the curve and changing its shape. B-splines are smooth, even at edges, making them popular in graphics. However, their continuous nature makes learning non-smooth functions challenging, and their recursive properties decrease computational efficiency. Critics argue B-splines may not be necessary, and that recursive properties can be avoided. So, who wins? CAN or MLP? Current results are mixed. CAN appears more parameter efficient and interpretable, but it's not yet tested on sequential data, which is critical for language models. While CAN outperforms MLP in specific tasks, concerns about overfitting remain. Despite being 10x slower to train, CAN's efficiency might still offer significant advantages for certain applications. It uses 10x less RAM, and a 10B CAN model could rival a 100B MLP model. There's still a lot to explore. CAN shows promise for parameter efficiency and interpretability, opening doors for engineering and physics applications. However, it's difficult to train, and comparisons with MLP are sometimes flawed due to improperly trained MLP baselines. Early experiments show CAN performs on par with transformers while using fewer parameters, but it's still in its infancy. Researchers need time to optimize and test its scalability. In summary, CAN is an exciting theoretical advancement. It could pave the way for more efficient AI models as we approach compute limitations in scaling MLPs. Stay tuned for updates, and don't forget to check out my newsletter for easy-to-digest AI research news. Thank you for watching, and I'll see you in the next one.